All right, good morning, everyone. Hope you guys all had a nice and restful weekend. Just wanted to go over test topics. We have a test coming up. It'll be on Thursday, so we'll have 2 days to review. It was Wednesday, but pushed it to Thursday. And want to go over the test topics with you. This document is on my website under today's date, so you don't have to, write everything down. But I do want to go over what to expect on the test. And then I want to go over, show you a couple of the resources that I have on my website. Make sure that you know about those if you want to take advantage of them. So first up, we want to make sure that we know how to solve differential equations, find particular solution. So we've been spending a lot of our efforts, our time with that every day. I'm hoping to do at least 1 or 2 of these problems, so that eventually it'll become more comfortable and more recognizable, and you'll know what the patterns that you're going to be seeing and following. Okay, now, so we'll practice with that today. We'll see a couple of variations of differential equations. We also need to be able to find tangent line equation based off of the differential equation. So all we need is order, pair, and slope. And differential equation is our slope formula, right? From there, from the tangent line equation, we can also find an approximation using the decimal that's given. So we just plug the decimal into that tangent line equation, and we'll practice some with that today. Differential equation word problem, something in the form of y prime equals ky, which we know is going to turn into the exponential growth or decay equation, y equals ce to the kt. And we know with these problems, really, we're skipping a lot of the calculus because we're jumping from the differential directly to the equation. So we're just solving or taking the information that's given, data that's given, we can put into order pair form to help us organize that. And then we can solve for C, we can solve for K, and then we can use our updated equation to make predictions at specific time values, or use find out the time period when a particular value is occurring. Okay, we'll practice some with that today. Yeah, and then the other scenario is where you're given order pair of that helps you find K, but then you have to go backwards and solve for C. So we'll look at both scenarios of that over the course of these next few days. Slope fields. If I give you an empty slope field, ask you to fill out 6 to 10 points using the differential equation. Okay, we'll practice some of that. And then also slope fields where I give you a filled out slope field and you have to match it with the appropriate differential equation. Okay, we may not get to that today, but either tomorrow or Wednesday we'll practice that. And then the rest are mainly 5.2, 5.5 quiz topics, except the inverse trig. That we did that on Friday. Okay, but natural logs, synthetic long division, use substitution, being able to recognize that's from 5.2. Trig integrals, new and the old integral rules. Sometimes some of the trig rules involve natural log. And also a little bit of use substitution. That's also for 5.2. Exponentials in the form of e to the u and a to the u. That's a lot of times that's use substitution as well. That's from 5.4, 5.5. And then the new topic that we did on Friday, inverse trig integrals, where there's a certain way that we have to look for matching that type of a problem. If the denominator that we see has a degree that is higher than the numerator by 2 or more, we know that's potentially a good fit for inverse trig. We have to get the denominator to show parentheses so that we can pull the a and u value appropriately. And finally, if the denominator is not in vertex form, if it's a standard form, we have to go through completing the square to get that denominator to be in vertex form, which we can pull the u value a little easier. Okay. But today we're going to focus mainly on topics 1 through 3, and then we'll get to more of the quiz and other slow field problems tomorrow and Wednesday. Okay. Any questions about test topics? All right, I want to just briefly show you on my website as well, just those resources there. So under today's link, this document that I just got through going over with you, I have it up here on my website if you want to look at that more closely or have a copy of it. It's there. I gave back your quizzes. I returned them to you. If you took it on Teams, I returned those to you as well. If you have questions about the quiz I made a help session video. You can click on that, went over each type of problem on the quiz. It may not be your exact version, but I did go through the steps. So hopefully that will help you if you're struggling with any of those problems on the quiz. But you can also reach out to me and I may be able to do some help sessions over the next few days as well, going over quiz and test topics. Over the course of this unit, I also made these resources, these references that you may find helpful. So I just decided to combine them all together into one location, so it'll be easy for you to access them. First, I have the Chapter 5-6 derivative integral rule sheet. Do you want to take a look at that, or if you want to print that out as you're working through your test review, I think that'll be good. But if not, I will be attaching it to your test, so you'll have a copy of that attached to your test. Integration technique checklist. The full list is here. That means I included the 5.7 with methods involving inverse trig integrals. Right? So just being able to organize your checklist so that you know to look for expansion, power rule first. If that doesn't work, then use substitution, then change a variable, then is it long division, is it synthetic division, is it inverse trig? So I just kind of put it all, organized it all under one document with a checklist. I also made integrals visual comparison handouts. I think I went over this with you where sometimes rational functions, they all kind of look the same, but looking at distinct properties such as how the degrees between numerator and denominator are related to one another, which one is higher, which one is lower, and if it's higher by 2 or more degrees, right? Those are things that help us identify potential methods to involve for those integrals. And then finally, I'll also have a step-by-step walkthrough of the differential equation steps. Okay, so feel free to print those out if you find that those will be helpful. All right, so let's go to our test review. Okay, the print is really small here. I'll show all the work on a separate sheet. All right, so oil is being pumped continuously from a certain oil well at a rate proportional to the amount of oil left. So we have a rate proportional to the amount present. So that's in the form of y prime is equal to ky. And we know what the result of that is, right? That's always going to turn itself into y equals ce to the kt. But sometimes we may have different variables representing that dependent variable. It could be y, it could be p for population, it could be r for radium, b for bacteria. All right, so if you want to do y, that's fine as well. I'm going to just let y represent the amount of oil. But ultimately, we know what equation we're working with. Okay, so we're just skipping the calculus part because we know this is going to turn itself into that. But we have information here that can help us make some predictions here. We know that initially there's 1 million gallons of oil in the well. 6 years later, there's 500,000. So we created our equation. That's part A. I'm going to change part B though. Instead of at what rate, we're just going to find how much oil there is when 600,000 remains. So find time t when 600,000 gallons remain. So we know that I like to create order pairs to kind of help organize my information, and then through a series of using these order pairs, we can update our equation piece by piece until we get to the point where we have a specific equation and we can use it to solve our problem. Okay. All right, so we like to start off with some order pairs here. We know that our order pairs will always be time followed by whatever our dependent variable is. So we'll let t represent time. We'll let y represent the amount of oil in the well. We always like to involve 0, right? 0 is going to help us a lot. So anytime we can have 0 as a time, as a starting point, the earliest starting point that we have is when there's 1 million gallons in the well. So we'll let 0 represent time in years, and then 1 million for, oops. 1 million gallons of oil at that given time. 6 years later, there's only 500,000 remains, so half of it is going to be gone. And finally, find a time when there's only 600,000 remaining. So this is more straightforward in the sense that we can use the first order pair to solve for C, use the second order pair to solve for K, and then once we have our C and K, we can find that last piece. Okay, so this can find C for us. This can find K. And then we can use the last order pair to put in to our specific and our final equation. All right, let's involve that order pair, first order pair. So 0 in for t, 1,000,000 in for y. We know e to the 0 is just going to be 1, so we know c is just going to be 1,000,000. Okay. Update our equation, replace the c with the number that we just found. And then once we have that update, we can move on to the second order pair. Okay, 6 in for t, 500,000 in for y. Divide both sides by 1,000,000. Eventually, we have to solve for k, but we'll take care of the coefficient out in front. All right, conveniently, all that's just going to reduce to 1/2, which I'm going to use 0.5 to make it easier to put in the calculator later. Okay, so it works itself down to easier numbers to work with here. All right, I want to solve for k, but k is sitting up in the exponent, so what can we do to bring it down? Yeah, let's have that natural log show up. Then that 6k is free to move between those two locations. Okay. Take the natural log of both sides. Okay. 6k comes down in front. Natural log of e cleans up to be just 1. Divide both sides by 6. Okay, we have our k value, but we're not going to put a decimal in for that, right? We're going to leave this as an exact value to improve our end results approximation to be as accurate as possible. But we should now be able to create our full particular equation with the data that is presented to us. All right, so now we have our updated equation. We can now make our final prediction here. We can find out using this equation how long it will take before 600,000 of oil remains in the well. So 600,000 in for y, and then I can solve for t. Okay, divide both sides by 1,000,000. Yeah, same process as before, right? Natural log, and then we can solve for t. Again, our variable is sitting up in the exponent. Natural log will help allow us to bring that down. Exponent comes down, and the rest calculator will help us with it. Divide both sides to isolate the t. Okay, so this is what I have entered in the calculator. Natural log of 0.6 divided by natural log of 0.5 over 6. Right? We know it's somewhere between 0 and 6 years, because 6 years is when half remains. This is more than half, so probably closer to 6 years than it is to 0. And if we just look at that number, right? Just do a quick check. That makes sense, right? Yeah, I think with word problems, it's always good to just look at the number real quick. You know, look at the context of the problem. Does it make sense? If it makes sense, then I'll give you some assurance that you didn't make a mistake that was easy to catch. But let's say you got something like 8 years or 8 point something. You know, something didn't quite go right, right? But if it's 6 years to reach 500,000, it shouldn't take that long for it to be 600,000. So. Okay. Any questions? Part C is similar. It's just asking how long will it take before there's only 50,000. So same idea. We're just now putting in 50,000 in for y and going through that process. Ends up being around 25, 26 years. So that makes sense, right? If it goes all the way down to 50,000, that's going to take some time before it gets there. So, but you can check the key. You can work it later if you like, but just this, I just want to be able to go through the process with you once. Okay, no questions with one. All right, let's look at number 2. Number 2 says, consider the differential equation dy dx equals x squared times y minus 1. On the axis below, sketch the slope field for the given differential equations. I'll only be asking you to do maybe between 6 to 10 points. Won't be as many as that. But let me just do a couple of points just to make sure that you guys are good with knowing how to create differential equation or slope fields for specific points. So I'm just going to target a few points and just have us practice through it. Let's say we want to target this point. That order pair is at -1, 3. So we just take that order pair, put it into our slope formula. In return, we'll get a slope, we'll get a number, and we'll translate that number into some slope expression. Right? Positive, we'll make a positive slope. Negative, we'll make a negative slope. 0, we'll make a horizontal line segment. And if it's undefined, let's say it ends up being like 10 over 0, then what would you do? Good, leave it blank, right? Don't put a vertical line there. I know we associate vertical line with slope undefined, but for slope fields, we'll just leave it blank. Okay, so let's practice that here. So let's say dy dx. I'll use the space for part C here. Okay, put it into my x squared y minus 1 formula. -1 in for x, 3 in for y. -1 squared is 1, 1 times 2 is 2. So we're going to create a slope that we think represents 2, and we'll put it right through that order pair. Okay, let's practice another one here. Let's try this point, -1, 1. Okay, dump it into the differential equation. -1 squared times 1 minus 1. 1 minus 1 is 0. Anything times 0 is 0. So through this point, if I want to slope 0, I want a horizontal line. Part B is asking to generalize where the positive and negative slopes are. So let's not worry about this. Yeah, we'll see that on the test. Any questions with creating slope fields? I just did 2 points just to make sure that we understand how to go about that process. Okay, the important thing here in this problem is this part C here, finding our particular solution. So this is what I want us to be really good at here. Okay, so I'll put this on a separate sheet so we can kind of have enough room to work. Part C, find the particular solution given condition order pair 0, 3. Let me rewrite the equation here. All right, so we know we're going to go through our steps. We know we want to separate our variables. There's no need to rewrite. There's no y prime here, so we're just going to, we have that descriptive differential variables there. So first thing, I want my dy dx's locked into their right slots. If I cross multiply, I can get that to happen. And then we can worry about how we can get those, our full separation of variables here. Okay, cross multiply. I'm going to target the dy first because I want my dy to be on the left side. Okay. So we have y's on the left. We have dy and dx locked in. That's the first goal. Let's make sure those are in the right slots. And now we got to take a step back and ask, do we have full separation of variables? Okay, we have one thing away, right? So what needs to be moved?
We just divide by y minus 1.
Good, divide by y minus 1. The parentheses are there to help you. So if we want to move the y, we're going to move everything inside the parentheses along with it. So Okay, 1 dy over y minus 1 equals x squared dx. Do we have full separation of variables?
Yes.
Now we do. Okay. Want to point out a couple things here. Just trust your algebraic skills, right? If you have x's or y's in the denominator, that's where they should be. Don't just move it up. If that's where it is, then that's where it belongs. We have rules that can handle that variable in the denominator. Second thing is, as a reminder, the parentheses are there to help you. So do not distribute the x squared at the beginning. If you do, you lose your ability to separate the variables at the beginning. So if there's a parentheses left later in the problem after you separate the variables and you're trying to discover the integral rules, then you can feel free to distribute if you need to, but not before the separation of variables. All right, so we have separation of variables. I'm going to rewrite this in the form. Maybe it's a little bit easier to read. So I'm going to push that dy out in front. Helps us recognize our integral rules. Right, so how would you approach the left side?
Substitution.
Yeah, use substitution. Now this is a fairly easy use substitution. So if you want to jump from this directly to the integral and just skip all the notations of writing out the u equals, I'm okay with it. Okay, but I'll still show it in case you want to just go through that process. Okay, replace the y minus 1 with u, replace dy with du, and we can see it matches with our integral rule for natural log. Becomes natural log absolute value of u, and then replace the u back in terms of the original variable. So if you like, you can jump directly from here to here if you're comfortable with that. So you don't have to write all this down if you don't want to. All right, what about x squared dx? What becomes of that?
X cubed.
Power rule, right? So not much difficulty there, and then plus c. So I'm going to put a box around here because I want to show that this is the most important part of the problem. If you can get to this part of the problem, you've earned the majority of the points. I would say maybe 80% of the points you've earned. And the rest is just cleanup. The rest is just, can you solve for y? Can you solve for c? Okay. And even if you mess up after this, I'll still look to give you partial credit, right? This is what I'm after. This is the most important part. Same thing on the AP exam. If they ask you for a particular solution, the majority of points are going to be earned up to this place here. All right, so let's reset. We know we have to involve solving for y. We have to involve solving for c. But I'm going to hold off on the order pair or solving for c, because I see natural log. So natural log, typically I like to wait a little longer because I know that things will clean up in a lot. The general equation is going to be a lot easier to work with. So I'm going to wait for my general equation before I solve for c. Now, if I see a y squared or y cubed on the left side, then typically I like to solve for c a little earlier, because I know there's a square root coming up and I want to get to my c value before it gets stuck inside that square root. All right, so we'll raise both sides, e as the base. Left side cleans up to be just absolute value of y minus 1, e and natural log. They undo each other. Okay. I can separate that c away from the first part of my expression. Becomes a multiplication. And we know e to the c is just another way of saying times c. I'm going to pull the c out in front. I can drop the absolute value but absolute value has plus or minus represented inside of it, so it has to be balanced out on the other side. So plus or minus will show up. We know C is just going to take in plus or minus, so there's no need to write plus or minus in front anymore. And then I'm going to add the 1 to the other side. Now notice that there's no plus C in our answer. The C is coefficient in front, so that plus 1 is going to have to stay there. We can't just let that plus 1 disappear. Now if there's a plus C, we can have that plus 1 absorb into that plus C, but being multiplied, that plus 1 will have to be part of our general equation, or sorry, yeah, our general equation. So if you look, this is a lot easier place to work with than this one. So I would much rather find my order pair here than earlier. So now I can involve my order pair. And then I'm going to solve for C from here. Okay, so 3 goes in for Y, 0 goes in for X. We know e to the 0 will just become 1. Subtract 1 from both sides, we get 2. And now we have our updated C value. We're going to put it where we initially made that substitution. Okay, careful where you put your 2 into the equation, right? There's all these other equations that have C's in it, but you're only targeting the one that you're actually working with in terms of the order pair that you're substituting in. Okay, there's our specific equation. But priority, right? This is what I'm really after. This is nice, but if you mess up here, you won't lose a lot of points. And even if you do, I'm going to look for ways to give you partial credit. So like this is what's most important. Okay, questions? All right, let's move on to the rest of this problem, which is finding equation of tangent line, and then also linear approximation. Okay, so let's do part D here. But I'm going to change this a little bit to make it easier, because this is not going to give us a full, it's going to wipe out a lot of terms. And I feel like we can get a better picture of a full problem if I use another order pair. So I'm going to update this. All right, so first things first, tangent line equation. What information do I need for tangent line equation? And point. Okay, so the point is given to us, so that's good. All right, how can I find the slope?
The original equation.
There we go, right? Your differential equation, that's your f prime, that's your slope formula. Okay, there's my point, there's my slope. Put into point slope form. Okay, so here's my equation. Going to move the 0, or really I'm just dropping the 0. Right, so there's my tangent line equation. How do I do linear approximation from here? Yep, that's all we do, right? So linear approximation, it sounds complicated, but really you're just updating your tangent line equation to approximate a specific value. You're just plugging a value in. So exactly right. We'll take that 1.2 and insert it into the x. -1 times 0.2. Negative 0.2. All right. Everybody good with that? All right, let's do one more problem. And we're going to go to number 3, which is another differential equation. But we're going to look to see if we can be more comfortable for problems that don't have x's and y's. What if there are other variables? Are we able to adapt and still solve? Right? Does anybody still need part D? Okay, here's number 3. Print is really small, so I'll write everything out again. It says, let v of t be velocity in feet per second of a skydiver at time t seconds where t is greater than or equal to 0. After her parachute opens, her velocity satisfies the differential equation, dv over dt equals -2 times v plus 16, with initial condition v of 0 equals -50. Okay, so we're going to solve this differential equation, but I want to talk about how to make that connection between x's and y's and other variables and not to be thrown off by other variables. So the big thing is that if you see variables that are not x's and y's, then it'll have to be t and something else. Okay? And the independent variable that will always be for other differential equations will always be time t. Okay? And which means that the variable that you don't recognize could be v, it could be w, it could be z, it could be q. That's your y variable. That's your dependent. Okay, so that means because we put x's on the right and y's on the left, for all these problems, you're going to put t on the right, and what other variable that you don't recognize, that's your dependent. That's going to be on the left side. Okay. Okay, so we want to do this. We want to treat our t as how we would treat x's. And then treat your v as you would treat your y's. Okay, so now that we have that basis, let's see if we can work towards separating the variables. So your steps will be all the same. You just have to kind of get used to these other variables here. So cross multiply, right? I want to lock in those differential variables in the correct locations. So I'm going to target the v's first. So 1 dv. Okay. I know a lot of times you're not going to achieve full separation just by cross multiplying, but it will help you make progress, right? You should get your differentials kind of locked in to their locations. So v's on the left, t's on the right. Do we have full separation yet? Okay, so one piece needs to move, and that is, okay, v plus 16. All right, let's do that. Now, we talked about how we want the left side to be as bare, as minimal as possible. So we want the dv, we want the v. Here, the 16 has to come along with it, right? It's part of the parentheses, so we can't do anything about that. But we can do is that -2, right? That -2 is going to stay on the right side. We're not going to move it to the left. It's not wrong if you do. It's just ideally, if you can keep your left side as minimal as possible, it will just make things cleaner when you do have to clean up that left side. Okay. So we should recognize this, right? We should be able to see this as a full separation now. Right? V's on the left. Anything associated with t, anything left over, coefficient is on the right. So we can move into taking our integral. I'll push the dv outside to make it easier to recognize. Okay, again, use substitution, right? Similar to before. If you want to jump directly to the integral rule, because it's a relatively easy u value, you can. I'll show all the steps though. We recognize that as a natural log rule. Replace the natural log back in terms of v. All right, so if you want to go from here to here, I'm perfectly okay with it. You don't have to write all this down. Now, if it's anything more complex than that, then we definitely need to show the steps. But these are, we save some time if you're comfortable jumping from this point to this point. All right, how about the right side? What does -2 dt become?
Negative.
Good, -2t. We don't put -2x, right? Because the dt tells us the variable that we're working with is in terms of t. And just as a reminder, the reason why this becomes -2t is because this is really sitting at -2t to the 0 power. And then when we go through power rule, we make that value rise by 1. So that's why it's -2t. So I'll put a box around this because we've accomplished the majority, accomplished the goal of this problem, the majority of it, which is getting to that general equation, taking the antiderivative, getting that plus c to show up, and now the rest is just cleaning up. Okay, so let's reset. I'm going to put this back at the top here, and then we're going to solve for c, and then solve for v as well. I know I have to eventually involve that order pair 0 and -50, but again, I see natural logs, so that's just going to cause me to want to solve for v first, get that all cleaned up before working in my order pair. Raise both sides, e is the base. Okay. We know e to the c just becomes a big C. Drop the absolute value. Pull the c out in front. We know dropping the absolute value is going to cause balance on the other side with a plus or minus. Plus or minus can go away because the c will just suck that in. Get v by itself, subtract 16. So now that I have my general, my general equation, I'll much rather plug in my order pair here than up here with the natural log. So now I'm gonna so 0 is my t, negative 50 is my v value, velocity. So negative 50 in for v, 0 in for t, and hopefully that will help us get to the c value that we want to target. E to the 0 is just 1, so I'm just left with c to solve for. Add 16 to both sides. Negative 34. And now we're going to reinsert our c with the specific value. There we go. Okay. We're not going to worry so much about part B and C, being able to solve the equation, being able to solve for C. That's our focus. And then also getting used to these variables that are not x's and y's. Okay. So tomorrow we're going to focus more on the integrals, identifying rules, practicing with maybe the Trig rules that we haven't that we've just gotten introduced to it from last Friday, and maybe we'll do some slope fields as well. If I have a help session, I will let you know through Remind, probably in the mornings and afternoons starting tomorrow. But otherwise, hope you guys have a great day. See you tomorrow as we continue reviewing. Take care, guys.